Hi everybody. Today we're going to spend a little bit of time with 2.15. So let's get those notes out. And we'll just jump right in and start with them today. We'll do a little review here in a minute. But I really, again, today want you to read through these notes because he does a great job of explaining, what's going on. We've already kind of talked about semi-log plots. They're not hard at all. One thing I do want to emphasize though is in that box at the top of the notes, he says, with a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. So if you plot some points, if you have some data points, you plot them on your semi-log plot and it looks like a line, then that means your data was exponential. If you plotted it with a regular grid, it would have been exponential. So he's got an example there. Got some population numbers, and as you would imagine, it's exponential growth. But when he does it on the semi-log plot, plots exactly the same points on this different grid, look how linear that data looks, particularly after about the first 4 points or so. It really, really approximates a line. So example 1 says, how can we justify why an exponential model is appropriate for this population study? Well, the exponential model is appropriate because the semi-log plot is linear after the first, 40 years. And you can imagine in the first 40 years of anything, over a long term, things are kind of sorting themselves out. But after that, it becomes very, very linear. So that's how you can justify it. If the semi-log plot is linear, approximately linear, then the data was exponential. Okay, number 2. The number of people that have heard the joke is graphed on a semi-log plot where the vertical axis has been logarithmically scaled. And by the way, in this class, in this course, the only axis we scale logarithmically is the vertical. So you don't have to worry about anything getting funky or weird that way. Okay, so which of the following functions could be a model for P? Well, certainly, if you wanted to kind of take a long, more meticulous approach, you could actually figure out what those points are and try to come up with a model for that set of data points. But I think it's a little easier than that because if you look at those points, and remember, this is a semi-log plot, if you look at those points, they're linear, which means that the model needs to be exponential. So immediately, we can rule out A and C because they are not exponential. Now, to decide whether we think it's B or D, which are the exponential equations, let's look at some of the points and see which ones fit. So the first point on the grid would be 0, 2. And then the next one is 1, 4. And the next one is 2, 4, 8. Okay, now let's look at our equations and see what our options are. We know it's one of these. It's this one or this one. So I got 3 points. Which one fits all 3 points? Let's see. If I put in a 0, I don't get 2. If I put in a 0, I do get 2. So I think it's this one, but I'm going to go ahead and check. If I put in a 1, I get 4. If I put in a 2, I get 8. So this is the right option. So again, we use the graph to eliminate possibilities. We knew it had to be exponential. And then we just plugged in a couple points to determine which of those exponentials it was. All right. On the next page, some important notes. You're not changing the y values. We are not changing the y values. We're simply plotting them on with a different scale. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional. So this is from a coming example, but look at it. The equally spaced ones are proportional, times 10. These are not equally spaced. Excuse me. All right, which of the following graphs could represent these data? Well, let's look at it and see. Well, first of all, I have a huge problem with all these graphs except D. If this is supposed to be a semi-log plot where the vertical axis is logarithmically scaled, take a look at A. First of all, everything is evenly spaced. That is not proportional. Y is not proportionally spaced. Y is arithmetically spaced, linearly spaced. Same thing with C. All right, so let's look at, well, first of all, it can't be B because the Y values aren't high enough. They only go to 10, and we gotta go to 203. So the answer must be D. The answer has to be D. Certainly, just plot a couple points out of the chart. We've talked about that before, that whatever model you choose, and in this case it's a graph, the data has to fit that. So just plug some data in. All right, example 4, I set this up so we can plot these relatively easily. I do need you to kind of get that these labels, 1, 10, 100, 1,000, are powers of 10. So this is 10 to the 0th. This is 10 squared. Excuse me, this is 10 to the 0th, 10 to the 1st, 10 to the 2nd, 10 to the 3rd. That's what it means to be logarithmically scaled. All right, so 0 to 100 is going to be right here. So this is 100, and excuse my grid, it's not nearly as good as the one on the paper, but right there is where you're going to put point A. We'll label it 125. Okay, so here's 1, here's 20 and 30, so 25 is going to be in between there somewhere. 2, 7, so 2, 7. Right here. 3.2 800. So 3.2 800 will be right here because there's 1,000. So there's 900, so there's 800. And finally 4.6 and 1.5. So remember, here's 1, here's 2, so 1.5 is going to be right in there. Now remember, if you've got issues with any of this, you can come in anytime, you know, for office hours, we can talk about these. We can do a little review in class and talk about them, but there we go. There we go for that. All right. Okay, we've talked about that when we plot on a semi-log plot, sometimes we get a line. That means the original is exponential. So that there's a correspondence between the original exponential and the corresponding linear, okay? And that's what example 4 is talking about. So let's take a look at example 4. At first this might seem a little bit confusing, but it really isn't. I think we can figure it out. Okay, so we have to go back and get our data points. Now, when we are, the original data points that we're using, I'm not gonna write them all down, were these. But when I plotted them to get that line, I didn't plot the point 40, I plotted the log of 40. That's what I plotted. So like, for example, over here, this number was 200, I think. That is not, if you count hash marks or whatever, that's not 200, that's the log of 200. When I changed my y-axis, I didn't change my y values, but I changed my y labels. So now, on my semi-log plot, this is the log of 40, and the log is 60, and the log of 90 on the semi-log plot. The new y's, the rewritten y's. Okay, so if I'm going to write the equation of the line, it says write the equation of the line, then I need the slope. So the slope, average rate of change, is going to be the log of 60 minus the log of 40 over, remember, these are the x's. I'm kind of leaving these out of the mix now, over 2 minus 1. So that actually can be simplified using our properties of logarithms. This would be the log of 60 over 40 over 1. And 60 over 40 is 3/2, 1.5. So our rate of change on the semi-log plot, the rate of change is the log of 1.5, whatever that is. So I can go ahead and get that number. So 0.17609. Okay. Now, I need the rest of, I need my equation now. I have my rate of change, I have my slope, I need my equation. So I'm just going to use this first point right here, and I'm going to do point slope. Here we go. Y minus the log of 40 equals 0.17609, or maybe I'll leave it log 1.5, x minus 1. Okay, so y minus the log of 40 equals the log of 1.5x minus the log of 1.5. So I'm going to add, so y equals log 1.5x plus log 40 minus log 1.5. So I add this over here. And I went ahead and wrote it first because I don't want you to get confused about what's being subtracted. The log of 1.5 is being subtracted, but the log of 40 is actually being added. So I'm going to put those two together using my properties of logarithms. And that's going to be the log of 40 over 1.5. That's 40 divided by 3/2, or 40 times 2/3. That's 80 thirds. So in exact form, that is my equation. If we want to have numbers for it, I already did that one, 0.17609x plus 1.42597. Okay, so there's the equation of the line. Again, it's like you've always done. There's no, we're writing the equation of a line. What you have to remember though is, since the line is on the semi-log plot, the y values are adjusted. So we don't use the original y's, we use the logarithmically scaled y's, or the log values of the y's. Okay, so there's my, I guess parentheses there, my equation. Now, the next part says, what is the, using this linear model, what is the equation of the exponential model for the original data? Now, could we have used the original data and written the equation of the exponential? We absolutely could have. We've done that over and over and over again. We could take this point and write the equation. We could absolutely do that. However, the way he has set up the problem, it's easier than that. You could do that, but he wants you to use this. So remember, this guy right here is the log base 10 of 1.5. That's what this number is. So in other words, log base 10 of b is 1.5. Your b value is 1.5. And this is the log base 10 of a, using the format that is given to you. It says your equation is of the form log base 10 of b times x plus log base 10 of a. Well, b was 1.5, that's how we got this number, and a is 80/3, that's how we got this number. So our equation is 80/3 1.5 to the x. That is your linear equation. All right, a little tricky. Let's try another one like that. Found one over here. So turn to the page that says lesson 5.9 semi-log plots. So just flip a couple pages in your notes. And one thing I want to change, I put the quick notes in there like I try to do to reinforce what he's got in his notes. One thing I do think it's probably appropriate that I change is, up there in the quick notes, the very kind of last line, I wrote y equals log a plus x log b, which is exactly what he did. That's exactly what he did. I left out the base n because I know I'm using base 10. When I do a semi-log plot, I'm using base 10, so I left that out. But this number right here, or not that number, this number right here is the log base n of a. So our a was 80/3. And then x times the log base 10 of b. Okay, what I want to make sure we understand is that in this form, that y is not the same as this y. So I'm going to go ahead and put a little mark above that to remind myself that that's my new y. Remember when I had my table up here and I added on my new y's, log 40, log 60? Those were the new y's, not the original y's, the new y's. So when I write the equation of my line, I'm using the new y's. When I write the equation of my exponential, I'm using the original y's from the original data points. Okay, all right, well, let's look at this page, check your understanding. Okay, so they've got a scatter plot drawn, and it's a semi-log plot because they've got log values on their y-axis. How is the log of the number of attendees changing over time? Well, if you look at it, it's a little funky at the beginning, but basically that curve becomes very linear. okay? So the log values are changing linearly. Remember, this is a logarithmic plot. So your y's on the log plot are changing linearly. Well, what does that mean about the actual y values, number 2, or letter B? What does that mean about the actual y values? If the log values are changing linearly, then the actual y values are going to be changing exponentially. So if we had data points, which we could get from our graph, and we actually plotted them, not on a semi-log plot, but on an actual grid, like a real standard normal grid, the growth would be exponential. Okay, and then C, this is the one I wanted to look at. C says the equation for the line, they've already done the line, is 3.8525 plus 0.0957x. That is the equation of the line. Okay? And our job is to find the A and the B to turn this into an exponential equation. Okay? Guys, it's easy. I don't know what A is. I have no idea what A is. But I know that its logarithm is 3.8525. Because the structure of the equation is log A, that's like your y-intercept, log A plus log B x. This is like your slope, your rate of change. I have no idea what A is, but the log of A is 3.8. Well, wait a second, how can I find A? If I know that its log is 3.8, then don't I just have to raise 10 to the 3.8525 power? So wouldn't A be 7120.328? And similarly with B, I don't know. I don't know what B is, but the log of B, and again I'm in base 10, is 0.0957. So 10 to that power is your B. So what is your equation? Your equation is, remember it's an exponential, so it's A times B to the x, so it's 7120.328 times 1.2465 to the x power. And of course you could check that because you know, for example, that if you plug in whatever, some x value you want to plug in, you're going to get a y. And you can check that on the grid, but remember, the y values aren't being graphed on the grid, the log of the y values are being graphed on the grid. So you have to be careful about that. Yeah, let me just do one just to kind of show you what that means. Let me just pick a point. I guess I can use 0. So if I plug in 0, I'm going to get 7120.328, right? Because that's just one. Now, on my grid, clearly at 0, the point that's plotted is not 7,000. The point that's plotted is the log of 7,000. So what's the log of 7120.328? About 3.85. So the point on my graph should be 0, 3.85. Well, look at your graph. Does that seem about right? Yeah, it does. So again, you can always check, but you gotta be careful about what y you're checking. This equation is going to give you the actual data point, 7,000. Your graph, the semi-log plot, is going to plot the log of your y's, the log of 7,000. Okay, let's do a quick little bit of review. So go back to your notes. I'm sorry about all this flipping around. But after the 2.13 notes, there is a page labeled 2.13 at the top, and then it says Solving Logarithmic Equations, Big 10. Okay, so this is a page in your notes, right after the 2.13 notes. Right after the 2.13 notes. There's a page, it says Solving Logarithmic Equations, Big 10. Okay, so let's find that. And he's made this kind of a little game, or wherever I got this, Calcmedic made this a little game. We're going to solve the equations, and the answers are going to be the digits 0 through 9, only used once. So obviously, if you have two equations with an answer of 5, you're wrong somewhere, because each one is only used once. All right? So this is review. Good review, necessary review. We've got to know how to solve all kinds of equations, including logarithmic ones. Okay? So we'll subtract 1. I know you can do these on your own. Most of you are super duper good at this. We'll divide by 3 and log roll. So 2 to the first equals x. So that one is 2. Keep track here. Alright, so that's problem number A. Alright, here we go. Second one. First thing you're going to want to do is put those two logarithms together. You guys, you can't solve the problem if you have two logarithms on the same side of the equation. So we're going to put them together. And when we put them together, they're going to go together as a multiplication, because when logarithms are added, the numbers themselves are multiplied. So now I can log roll it, and it looks like x is 6. Technically, of course, when I square root both sides, I get plus or minus, but the base in a logarithmic expression, the base can never be negative. So that is just going to be positive 6. The next one is very, very similar. Very similar, because you have two logarithms being added together. And when logarithms are added together, it means the numbers have been multiplied. So x times x minus 4. Now we'll log roll it and solve. This is going to be a handy dandy little quadratic. So let's get it set equal to 0. And it does factor. You could, of course, use the quadratic formula or complete the square. This would be easy to do. But it does factor, so I'll go ahead and factor it. And it looks like x is 8. Now, I am not sure why they felt the need to include positive solution only, because this answer wouldn't work anyhow, because in the original problem, which starts out like this, the original problem, you can't put a negative here. That doesn't work. So that would be an extraneous root anyway, and 8 is the only answer to the problem. Even if they don't say positive solution only, it is still the only solution. All right, D, straight up log roll. There's no work to do there. We're just going to log roll it. And again, we have a little quadratic, it's 9, which again factors beautifully. And again, because of the, wait on this one, be careful. On this one, I think we need to say positive solution only, because when I plug in -4, this would be 16 minus 4 minus 3, which is positive. So that is not an extraneous solution. If this were in another situation and we were just solving, both of those would be answers. Both of those are acceptable. But they do say positive only, so I'm going to pick the 3, and that's the answer to D. So again, let's make sure everybody's clear on, if you're walking down the street and you find equation C, no directions necessary, just solve it. Equation C, the only answer is 8, because that would be extraneous. If you found equation D and you solved it, the answer would be both of these, because even though that's negative, when I plug it back into the original problem, I'm taking the log of a positive, and that's the key. This has to be positive. Okay, and E is just a log rule. So 5 to the first equals 3x plus 2. Looks like x equals 1 for that guy. So this is E. Now, F is an ln problem, but logarithms are logarithms. This is just a different base. All the properties are the same. So again, we have to put those two together. So I'm going to multiply x minus 3 times x plus 4 and 3 ln 2. So I'm going to have ln FOIL x squared plus x minus 12 equals ln 8, because a number out in front of a logarithm is actually an exponent. So ln 8. Now this one's a little different, no log ruling here, because we have ln equals ln, so x squared plus x minus 12 equals 8, another quadratic, x squared plus x minus 20. Factors, somebody's really rigged these nicely, plus 5 minus 4. So I got -5 and positive 4. I'm going to look back at the original problem. I can't put -5 in there. -5 doesn't work. Can't put it in. So that's extraneous, and F is 4. One more time. I am not canceling out this number because it's negative. You can have negative answers. I'm canceling this number out because when I plug it back in to the original problem, -5 right here, that would mean taking the logarithm of a negative number, and that is what's not allowed. All right, G is a straight log rule, 7 to the x equals 1. The only thing x can be is 0. So G is 0. H, again, we have two logarithms, but this time they're being subtracted. So this is going to be a division problem. When you are subtracting logarithms, you're going to divide the numbers and then log rule it. So 2 cubed is 8. We'll multiply this over to here. And solve this handy-dandy linear equation. So it looks like 4x equals 20. I got 5. That is letter H is 5. Ooh, look at I. This is interesting. Now remember, the base is 10. Common logarithm. It doesn't matter what this is, I can log roll my problem. So I'm going to start right here with this guy. The log of something is 0. So 10 to the 0th equals the something. So again, it doesn't matter what this is. Whatever it is, 10 to the 0th equals that. So 10 to the 0th equals the log of x plus 3. Well, 10 to the 0th is 1. This base is also 10, so I can log roll that. And it looks like x is 7. The I. Hopefully, j is going to be 9. Again, double logarithm, we aren't going to panic about it at all. We aren't going to panic about it. We're going to start on the outside and work our way in. Think about it as the log of something is 0. So 10 to the 0 is the something. All right, I think here I'm going to go ahead and subtract that 1. Divide by 5. And then 3 to the 4th is x squared. So it looks like technically, well, x could be plus or minus 9. And when I look back at the original problem, it could be plus or minus 9. Because in the problem I'm squaring it, so it become 81. So they said take only the positive solution. So that is 9, and that is j. Alrighty, dighty. Good job. Let's get that done. We'll be ready to rock and roll.